This is my research talk. I call it More Predictive Density Functionals, Symmetry Breaking, and Strong Correlation. And I'll try to link those three things in my talk. First, I want to acknowledge discussions that I've had on symmetry breaking and density functional theory with Alex Zunger and Mark Peterson, and also with Hardy Gross and Janwei Sun. And I've had many collaborators in this work. Some of their names are listed here. Going back to my tutorial talk, there are two first principles approaches for materials prediction. Materials here includes molecules. There's the, as well as solids and liquids, there's a correlated wave function theory, which promises the right answer for the right reason, but at great cost and mainly for small systems. And there's the density functional theory, which promises almost the right answer for almost the right reason at almost the right price for almost all systems of interest. And it's the density functional theory that I'll be talking about primarily today. Now, the exact cone-sham theory, the exact cone-sham density functional theory would describe the ground states of all materials, whether those are simple materials or complex materials. I'm going to define complex materials as materials in which many different states compete energetically to be the ground state. There's a close competition between these states, and so they're particularly challenging. The complex materials are particularly challenging for density functional theory. And some of these complex materials are strongly correlated materials like transition metal oxides. Others are more familiar materials like water. So water is a complex material because in liquid water, there are many different possible hydrogen bond networks that compete with each other energetically. The proper description of liquid water requires a good density. Now, we know exact expressions for the density functional for the exchange correlation energy. There are expressions from David Langreth and myself, from Mel Levy, from Elliot Lieb, and others. And the exchange correlation energy plays an important role. It's nature's glue that bonds one atom to another to make a molecule or a solid. But the evaluation of these exact expressions, exact formal expressions, is impractical. And in practice, the exchange correlation energy as a function of the density must be approximate. But the existence of exact expressions permits the derivation of the exact mathematical properties of this functional, which can be used in the construction of approximations. So the challenge of complex materials is to make the approximation accurate enough and reliable enough to capture the small energy differences between competing states or phases. One approach to complex materials in condensed matter physics is through model Hamiltonians with fitted parameters. They're popular and useful, but they're really not general enough and not material specific enough for materials discovery. If you want to just be able to discover new materials with useful properties, you cannot rely on fitted parameters. There are two different but mutually exclusive ways to construct density functional approximations. These ways can be applied separately or together. The first one is popular in chemistry. The idea is to fit to a data set of real bonded systems, typically molecules, typically also a few of the exact constraints and appropriate norms are satisfied. For instance, almost all density functionals have the correct uniform density scaling of the exchange energy. So in that sense, they have some constraints, but not perhaps very many. So the approach of fitting to a data set is an interpolative approach, I would say. And it's often the most accurate approach for systems that are similar to those that are fitted in the construction. And machine learning is a new and powerful way to do this fitting. A second approach to construct density functionals is by the satisfaction of exact constraints, which are the known mathematical properties of the exact density functional, like equalities, bounds, scaling relations, limits, and so on. And many of these exact constraints have been derived by Mel Levy or Elliott Lieb. And we can also use, in the second approach, appropriate norms, which are non-bonded systems for which the approximation should be very accurate. The first appropriate norm was the uniform electron gas, which is enough by itself to construct the local spin density approximation, the first rung of the Jacob's ladder. This first principles approach, the second approach is more of a first principles approach, and it's more widely predictive. It predicts, but it doesn't fit bonds because no bonded systems are used in the construction. And the question you can ask is how accurately this approach can predict over the immense space of possible bonded materials. So some computationally efficient semi-local density functional approximations that are constructed by the second or constraint-based approach. The first one is a local spin density approximation, which comes originally from Kuhn and Sham in 1965. They were inspired by the Thomas Fermi approximation for the kinetic energy, which is also a local density approximation. They made a similar local density approximation for the exchange correlation energy. In this system, the uniform gas is the appropriate norm. The input is the exchange correlation energy per particle in an electron gas of uniform spin densities. That was found accurately in 1980 by Sepperly and Alder in a quantum Monte Carlo calculation. And it was parameterized in various ways, and perhaps the most constraint satisfying parameterization is the Perdew-Wong 1992. The local spin density approximation inherits from its uniform gas appropriate norm the satisfaction of 9 of the about 20 known exact constraints. On the second rung of the Jacob's ladder, we have the Perdew-Burke-Ernzerhof generalized gradient approximation from 1996. It was constructed to satisfy 11 exact constraints and the uniform density appropriate norm. We always try to keep the uniform density appropriate norm. And on the third rung of the ladder, we have SCAN, the strongly constrained and appropriately normed meta-generalized gradient approximation to Janway, Sun, Adrian Wojcinski, and myself in 2015. SCAN satisfies all the 17 exact constraints that a meta-GGA can satisfy. And its appropriate norms include the uniform gas densities, but also selected closed subshell atoms. And SCAN, like PB and LSD, is not fitted to any bonded multi-center system. So whatever it says about bonding is a prediction, not a fit. So I'd like to say a little bit about the principles of the scan construction. There are some exact constraints that apply to all electron densities, such as the uniform density scaling property of exchange. But there are many exact constraints that cluster around one or two limits, either the limit of slowly varying densities, where we know gradient expansions, for instance, or the limits of 1 and 2 electron densities, where we know many bounds and so on. So simple functionals can be, GGA-like functionals can be constructed for each of those two limits. And then a dimensionless function of position alpha can be introduced, which is constructed. It's a dimensionless function that's constructed from the local spin densities, their gradients, and the positive orbital kinetic energy density from the cone-sham orbitals. And with the right combination of those ingredients, you can produce a quantity alpha, which can recognize 1 and 2 electron densities in which alpha is 0, or slowly varying densities in which alpha is 1. And it can also recognize density tail overlap regions where alpha is much greater than 1. In these density tail overlap regions, we have, for instance, for weak overlap, we have van der Waals type interactions. So scan interpolates between the first two regions and extrapolates to the third. And I'm going to list some of the successes and also some of the failures of scan. We'll start with the successes. Scan is much better than previous semi-local functionals for water and interfaces, water and solid interfaces. Water is a difficult problem, as I said before. For ferroelectrics, in which crystal lattice distorts to produce local dipole moments, local polarization, electric polarization. For the formation energies and ground state crystal structures of strongly bound solids. For the critical pressures for structural phase transitions of semiconductors. You put semiconductor under pressure and then the crystal structure can change at a certain critical pressure. Scan is also good for, scan by itself without any correction is good for some strongly correlated materials that standard density functionals normally do not get right, including manganese dioxide, which has many different crystal structures, and also the cuprate high temperature superconductors, where we get a fundamental energy gap in the pristine material, and as we dope the material transforms from an insulator to a metal. The gap closes under doping. We also get the right spin moment on the copper atom. We get stripes and stripe fluctuations, many other things from the scan functional without any additional correction or empirical input. You can also get geometric and mechanical properties of materials, including two-dimensional materials. You can get surface energies of metals accurately. On this slide, I'm showing you some results from a paper by James Furness and collaborators from 2018. They applied scan to the cuprate lanthanum copper oxide, or LCO, and also the doped cuprate LSCO, in which some of the lanthanum atoms are replaced by strontium atoms. And what happens here is that, first of all, if you look at the pristine material, and that's on the left, you see the density of 1 electron states as a function of 1 electron energy. In LSDA and PBE, lanthanum copper oxide is a metal. There is no gap. But that experimentally, there is a fundamental gap of about 1 electron volt. And when we apply scan to this material, we get the gap. And in fact, we get about the right gap. The gap opens up. You can see the structures of these materials. The structure of the pristine material is shown in by the second picture. The copper atoms lie in layers, and each copper atom in a layer is surrounded by an octahedron of oxygen atoms. And between the layers, we have the green balls that are the lanthanum atoms. And when we do 25% doping with strontium, we replace 25% of the lanthanums by strontiums. That's indicated schematically in the third picture. The gap closes, and the material becomes a metal, and that's where it is able to superconduct. So we don't actually capture the superconductivity because that's too delicate an effect, but we get a very good description of the underlying material in which the superconductivity is found. For molecules, SCAN has been tested on Stefan Grimmer's large GMTKN55 suite of 55 molecular data sets. And in 2017, that test was made, that data set was applied to a large number of density functionals available at that time. SCAN turned out to be the best embedded GGA tested. It was better than any GGA or LSDA. It was, however, outperformed by some of the hybrid functionals. SCAN actually outperformed some of the hybrid functionals, but some of the other hybrid functionals outperformed SCAN. You should realize that the functionals that SCAN was competing with were largely empirical functionals that were fitted to molecules, very much like the molecules in the GMTKN set. There is one set in GMTKN called the mindless benchmarking set. It's a set of artificial molecules. It takes 16 atoms. We test to see if they will bind to form a large molecule. And the binding in many cases is only metastable, and this 16 atom complex can, with the addition of some energy, break up into more stable, smaller molecules. So the interesting thing about this set is that none of these artificial molecules have ever been included in the fitting of standard functionals. And on that set, SCAN outperformed all the other functionals that were tested, including the hybrid functionals. So to me, this shows that the predictive power of the exact constraints. If you have a functional that satisfies many exact constraints, it can not only describe what familiar systems, but even unfamiliar systems and unusual systems. Now I'll give you the rest of the story. There are some systems on which SCAN was only somewhat better than previous semi-local functionals, modestly better. For instance, the band gaps of semiconductors and insulators, which are too small in LSDA and PBE compared to experiment. They're still too small in SCAN, but they're bigger. Okay, so there's a modest improvement in band gaps. For most of the transition metal oxides, other than the ones I just mentioned, SCAN still needs a core band self-interaction correction or a plus U correction, which can be, and the plus U is a parameter that can be found either empirically or non-empirically, but it's a material dependent parameter in any case. For most of the transition metal oxides, SCAN still needs a plus U correction to get an accurate result, but it turns out it needs a smaller value of this parameter than other functionals like LSDA or PBE. So SCAN is capturing more of the correct physics of these problems by itself. Then there's some systems, to be completely honest, there's some systems where SCAN is actually less accurate than the PDE-GGA or Laplacian level meta-GGAs. In a Laplacian level meta-GGA, you replace the Kohn-Sham orbital kinetic energy density as an ingredient of the exchange correlation energy by the Laplacian of the density. They have roughly the same information for many systems, but if you look, for instance, at the formation energies of intermetallic compounds, if you look at the magnetic properties of solid transition metals, or vacancy formation energies of transition metals like iron or platinum, it turns out that SCAN is actually less accurate than GGAs and Laplacian level meta-GGAs. And we interpret that in the following way. In a metal, the exchange correlation hole surrounding an electron is perfectly screened at long range. So the exchange correlation hole is very short range. And the metals are ideal for functionals that have very weak non-locality. They depend mainly on the electron density itself and perhaps its first gradient, but not on the orbital kinetic energy density, which is a more non-local ingredient. On the other hand, in semiconductors and insulators, the more non-local ingredients in SCAN produce more accurate results. Another problem with SCAN, it was not an accuracy problem, but a computational problem. SCAN made extra demands on the mesh for integrations over real space. And there were some problems to construct pseudopotentials for SCAN. And those problems were solved in 2020 in the paper by Furness, Sun, Kaplan, Ning, and myself with a functional called R2-SCAN. R2-SCAN is SCAN smoothed out in such a way that it doesn't have these numerical problems. It's just as accurate as SCAN, and it satisfies almost as many exact constraints. Instead of 17 exact constraints, I would say it satisfies 16.6 exact constraints. It doesn't get all of the fourth order gradient expansion for exchange that SCAN gets. So SCAN from 2015 and R2-SCAN from 2020 are meta-GGAs that are usually more accurate than a PDE-GGA, certainly more accurate for molecules, semiconductors, and insulators, for a modest increase in computational cost, maybe a factor of 3, something like that. So without being fitted to any multi-center bonded system, they describe diverse bonds like covalent bonds, metallic bonds, hydrogen bonds. They even capture intermediate range van der Waals interaction. They don't capture the long range of the van der Waals interaction, which is a truly non-local effect that semi-local functionals can never capture. Yeah, but often the intermediate range of the van der Waals interaction is the most important part of it for bonding. These SCAN functionals have been adopted by the Materials Project. The Materials Project is based at Berkeley. It's a website with the computed properties of about 146,000 known materials. All of the known solids for which the crystal structures are known experimentally are in the Materials Project. And their properties have been computed by density functional theory, originally by the PDE-GGA, but the Materials Project is now switching over to SCAN and R2-SCAN. It will take time to do that conversion, but they're doing it. Okay. So that's the first part of my talk about the scan and R2 scan meta-GGAs. Now, the second part of my talk is about symmetry breaking and strong correlation in density functional theory. So let me give you a little background on this. Quantum mechanics suggests that any isolated finite system has a symmetry unbroken ground state wave function. What I mean by that is that if the Hamiltonian commutes with certain symmetry operators, then you can find common eigenstates of the Hamiltonian and the symmetry operators. And those common eigenstates are symmetry unbroken ground states, for instance. The symmetry unbroken ground state wave function can be strongly correlated if the corresponding cone-sham non-interacting system has nearly degenerate ground states of the same symmetry. And the reason is that if you turn on the electron-electron interaction as a perturbation to compute the correlation energy, you will find that you get very large, unusually large correlation energies if you have degeneracies or near degeneracies in the non-interacting system. That's not always guaranteed, but it happens if you have degeneracies or near degeneracies, and you also have sizable matrix elements for the electron-electron interaction between the different unperturbed states. So standard density functionals capture what I would call normal correlation, the kind of correlation that's present, for instance, in the uniform electron gas or in typical molecules or typical semiconductors. These standard density functionals don't capture this strong correlation because they don't have any information about this degeneracy or near degeneracy. Except, of course, if you go to very low densities for the uniform gas, where you do capture some strong correlation. But a good density functional can often capture the ground state energy of a symmetry unbroken, strongly correlated state by yielding a symmetry broken, normally correlated state. If you break the symmetry, you probably break the degeneracies, and breaking the degeneracies breaks the strong correlation, takes you back to normal correlation. So if you look for solutions of the density functional problem that break symmetries, they may be able to describe these strongly correlated systems. And in some cases, I'll show you that they do. These symmetry broken ground states are not exactly true eigenstates in finite systems. Instead, they're states that have small energy uncertainties and thus long lifetimes. And the lifetimes can increase with increasing system size. Phil Anderson in 1972 wrote an interesting essay that I think many of you may have read called "More is Different." It was published in the journal Science. And in this essay, he argued that symmetries break when the time-dependent density or spin density fluctuations in the system, which are accessible in time-dependent density functional theory, drop to low or zero frequencies. So the idea is that you have in the ground state, even though the ground state is a time-independent wave function, it's really describing a system in which the electron positions are fluctuating all the time because the electrons are point particles. They can't form a truly uniform density, which is static. But instead, in the average density, there are strong fluctuations around time-dependent fluctuations around the average density. And when the frequency of those fluctuations drops to zero, the fluctuation can freeze out as a symmetry breaking, very much like the way ice freezes from water. Water is symmetric. When you lower the temperature, ice is formed, and ice has a broken symmetry because it has a crystal lattice. has special directions for the crystal lattice. So Anderson argued that, for instance, he's talked a lot about antiferromagnetism in the solid. Antiferromagnetism means that you have typically a solid with transition metal atoms. You find that some atoms are spin up and some are spin down with a regular lattice pattern. And he argued that that's a symmetry breaking that, because it occurs in a very large system, a solid, can persist for years. So we observe the symmetry breaking in large systems because it persists for a long time. I'm going to tell you about a calculation we did recently that supports Anderson's interpretation, or agrees with Anderson's interpretation. It's maybe a better way to say it. We know that in gellium, so gellium is a uniform electron gas. More precisely, it's a uniform rigid positive background neutralized by electrons. You throw in enough electrons to neutralize this uniform positive background, then you have gellium. And at normal and high densities, the electrons form an electron gas, which has the same translational symmetry as the uniform positive background. So the electrons themselves have a uniform density. And if you go to very low density, it's known that the electron density crinkles up in a so-called static charge density way. Oberhauser predicted this a long time ago. Later, it was found for gellium in the quantum Monte Carlo calculations by Sepperly and Alder in 1980. They predicted that this transition to a charge density wave occurs at low densities in which RS is between 65 and 105. RS is a density parameter. RS is roughly the average distance between electrons in the atomic units of Bohrs. So these are obviously very low densities. He also predicted that the wave vector was about 2.28 times the Fermi wave vector, which is a constant over RS. We studied this transition in two different ways. We looked at the dynamic density response function chi of time-dependent density functional theory for the uniform phase. And we also looked at the static response function, which is the zero frequency limit of chi. The basic idea here is that we have a uniform density, and we apply a weak perturbing external potential delta V, which is a wave. It's a wave with a wave vector Q and with a frequency omega. And we get a density response, delta N, that is proportional to this weak perturbation. And the proportionality constant is this density response function chi, which is a function of the density, or the RS parameter, a function of the wave vector, and also a function of the frequency. And you can find chi of RS, Q, and omega from a Dyson equation, which is the last line on this slide. Chi zero is the Cohen-Sham or non-interacting response function, which is known. That's the Linhard response function. And then we have another term where we have chi zero times an effective interaction between electrons times chi, the interacting chi. And that effective interaction between electrons is 4 pi over q squared. That's the Fourier transform of the Coulomb repulsion between electrons. And an exchange correlation correction called the exchange correlation kernel, FXC, which is also a function of RS, Q, and omega. So with the exact kernel, this equation is in fact exact. So what we did here was we modeled the exact exchange correlation kernel FXC of RSQ and omega to satisfy exact constraints. This work was done by Roginski, Nepal, Patarki, and Perdew in 2020. It's very much like the way we construct density functionals by the satisfaction of exact constraints. In this case, we used known exact constraints on FXC, and then we were able to construct the response function. And from where the response function diverges, that means that the uniform phase is unstable against the formation of a charge density wave, because it means that the uniform phase will have a finite response to an infinitesimal perturbation, which means that it spontaneously will form a charge density wave. So we looked at this problem in two ways. First of all, from ground state density functional theory, we looked at the zero frequency limit of the density response function, and we found that it diverged with our model kernel FXC. It diverges at q equals 2.28 kf, which is exactly the critical wave vector. And it diverges at RS equals 69, which is in the range of allowed values that are consistent with the Sepperly and Alder quantum Monte Carlo calculation. We also looked at this problem in a second way from the point of view of time-dependent density functional theory, in which we construct chi of RSQ and omega, and from it we construct the spectral function S of RSQ and omega, which is minus 1 over pi times the density times the imaginary part of chi. And we found that quantity is concentrated at zero frequency when the wave vector is the critical wave vector and the density is the critical density. I'll show you what sense that's true. But what we found is that Anderson was right, and that loosely speaking, the static charge density wave is a soft plasmon. It's a plasmon that drops to zero frequency. And I'll show you a figure that illustrates that. It's this figure. On the horizontal axis, we have the wave vector of the density fluctuation Q divided by the Fermi wave vector Kf. On the vertical axis, we have an average plasma frequency as a function of Q divided by the Q equals 0 plasma frequency of the metal, the uniform gas. And this average plasma frequency is defined by averaging over the spectral function the frequency of the density fluctuation of wave vector Q equals 2 pi over lambda in gellium at the densities, first of all, for real metals, blue, RS equals 4 corresponds to the valence electron density of solid sodium. There you can see that the plasmon disperses upward. So the plasmon starts out at the bulk plasma frequency omega p0, and as you increase the wave vector, the plasmon frequency just rises monotonically. When we get to low density, like RS equals 69, we see that the plasmon frequency disperses the other way. It disperses downward. At some point, the plasmon disappears as a collective excitation because the plasmon can break up into a particle whole pair. That's roughly here at Q over Kf equals 1.5, but we can continue with the dashed line by averaging over the spectral, averaging over the spectral function to take out the frequency, and we'll see that this quantity drops to zero frequency at Q over Kf equals 2.28, and then it comes back up again. But there's a critical point where the charge density wave appears, and it appears exactly where it should. Now I'm going to give you another example, which is more closely related to the scan functional. This is spin symmetry breaking in the singlet carbon dimer, the C2 molecule. So most sp bonded molecules are normally correlated and are well described by density functionals without any symmetry break. But the singlet or spin zero state of the carbon dimer is an unusual case. It is sp bonded, but it's strongly correlated. That's discussed in this paper by Alavi and collaborators from 2011. It's strongly correlated because there's a near degeneracy at the non-interacting level between two states that have the same symmetry. So there's an avoided crossing near and this occurs near the equilibrium bond length. It's not so unusual for this to happen in sp bonded molecules when you stretch the bond out very far. But this happens at the equilibrium bond length. The singlet C2 has a very strong correlation compared to other similar molecules. And the carbon atom, on the other hand, and the triplet C2 are normally correlated. The triplet C2 is the spin one excited state, first excited state of the molecule. And so this molecule has been studied by accurate correlated wave function methods, including the full configuration interaction quantum Monte Carlo, which confirm its strong correlation. Now, what does SCAN say about this molecule? We come to the next slide. If we do self-consistent LSD and PBE generalized gradient approximation calculations, the first and second rungs of the Jacob's ladder, if we don't let them break symmetry, and typically the only way you can get a system to break symmetry is by nudging it into the symmetry broken state. So if we don't do that nudging and we don't allow them to break symmetry, then these functionals really don't identify singlet C2 as a strongly correlated molecule. That's because they're not accurate enough. The strong correlation is significant, but it's still comparable to the error that those functionals make. For instance, the mean absolute error in electron volts for the atomization energies of 6 normally correlated small representative molecules. This is the so-called atomization energy 6 set. In Hartree-Fock with exchange only, the mean absolute error is 6.3 electron volts. In the local spin density approximation, which includes correlation, the error is reduced to 3.3 electron volts, but that's still big compared to the strong correlation singlet C2. In the PBE GGA, the error is further reduced to about 0.6 electron volts, but that's only roughly comparable to the strong correlation. It's only when we get to the scan meta GGA that the functional is accurate enough, where it makes a mean absolute error of 1/10 of an electron volt or a 1% error, an error that's much smaller than the strong correlation, that we can actually see that C2 is a strongly correlated molecule. If we do scan without letting the symmetry break, if we don't nudge it into symmetry breaking, scan gives a 1.4 electron volt underbinding for singlet C2, which is huge in comparison to the typical scan error of 0.1 electron for a small molecule. So on this slide, I show the scan results and the results of the other functionals for the atomization energy of singlet C2 at the equilibrium bond length for several functionals with and without spin symmetry breaking. So if you do LSDA, there is a difference, between there is a symmetry broken solution, but it only makes a slight increase in the LSDA atomization energy, which is too large anyway. When you go to the PBE GGA, the air without symmetry breaking is 6.0, and with symmetry breaking it's 6.7. There is a difference of 0.7. But if you go to the scan method GGA, you see that there's a big difference between the symmetry unbroken atomization energy and the symmetry broken atomization energy. It changes from 4.8 to 6.2, which is a 1.4 electron volt difference. And the final symmetry broken atomization energy is essentially the same as what comes from the full CI quantum Monte Carlo. That level of agreement may be somewhat accidental, but I don't think it's entirely accidental. If you look at what the symmetry breaking is, you see that in this molecule, which should be a spin singlet with zero spin density everywhere, the broken symmetry produces net up and down spin densities at different points in space, in C2, the net up and spin densities are now not on the ends of the molecular bond, but on the sides of it. That's an unusual feature of C2. This pattern was first found within the PW91 GGA by Mark Peterson in 1992. Okay, so we have a paper on that, which is going to appear in JPhys Chem. So now I've come to the end of my talk, and I'm going to give you my summary. First of all, density functionals for the exchange correlation energy of a many electron system become more accurate and more widely predictive, or maybe I should say they can become more accurate and more widely predictive when they are designed to satisfy more exact constraints and more appropriate norms. And SCAN is a good but imperfect, non-empirical, semi-local, and hence computationally efficient functional. Much of the full non-locality of the exact functional can be restored by making a self-interaction correction. I told you that in the strongly correlated systems, one needs a self-interaction correction. Plus U is often interpreted as an effective self-interaction correction. But I think one needs to make a real self-interaction correction by a modified Perdew-Zunger self-interaction correction. So in 1981, Perdew and Zunger proposed a way to make a self-interaction correction. I think that's a good way, but it needs to be somewhat modified to preserve more of the exact constraints of the underlying functional like scan. So we can if we can make a good self-interaction correction to, for instance, R2 scan, it doesn't lose the correct slowly varying limit. We may be able to get a good description of the strongly correlated systems, perhaps of all the strongly correlated systems without a plus U correction. And we're working on that. And finally, density functional theory with symmetry breaking is starting to correctly describe the ground states of strongly correlated complexes. Still a long way to go. And I think we need self-interaction correction to make this work well. And I'm not sure it will work well, but I'm hopeful. So I'd like to thank you very much for your attention. I think there'll be an opportunity to ask questions at another time.